Okay, I got it recording.
I appreciate it. Thank you.
Yeah, my question is how they integrated that. I still don't get it.
How do you integrate what? Say it again.
How when I put the 16 minus x squared in place of y squared, so I put y and square it, I don't understand how they got negative 1/4 and then 16 minus x squared to the cube divided by 3. I don't get it.
Okay. And then just minus 0, and we plug in a 0, right?
Yeah.
So 0 to 4, x over 2. If we square this, what's 16 squared? Is that 256? I don't know. Is it is? That'll be minus 32x squared and then plus x to the 4th.
Yeah.
And if we do go back and show that x over 2 to all those terms, just to make this a little simpler, so not working with the product, 256 divided by 2.
124.
128. So we'll have 128x minus 16x cubed plus 1/2 x to the 5th. And then from there, it's just power rule 3 times. So is that catch where you had trouble yet?
Yeah, I guess I didn't follow because
Okay.
what I did was I just squared the 16 and then I squared the x squared. So I had squared minus x to the 4th. That's what I did.
Yep. Don't forget to FOIL it. Yeah, always FOIL it.
All right.
Okay.
All right. Thank you.
Yep, no problem. Anything else?
Next, I actually have a question about next semester.
Okay.
Do we offer it as a 5?
No.
It's all new.
Differential equations is always a 3-hour class.
That's all. That's.
Yeah.
Otherwise, we're getting screwed in that sense.
Nope, and it's every school too. Actually, most other schools, when you go to them, Calc 1, 2, and 3 are usually 4-hour classes. We offer them as 5-hour classes here, but differential equations is like 3 hours everywhere. That's just a 3-hour class.
Gotcha.
So we're not trying to mess things up too much. All right, section 14.5, surface area. Another use double integrals. I mean, really what we're going to get down to is you can see the formula down here. So there's where we're trying to get to. But I like to try to explain where it comes from and try to put it into terms of what we're actually working with here. And we're doing the same thing we always do with integrals. Anytime you work with an integral with a double, single, we'll eventually get to triple integrals too. Anytime you're working with integrals, we're always taking something, splitting it into an infinite amount of much easier pieces to work with and adding all those together. And that's what integration does. It's a limit of an infinite sum. So we think about what we're trying to work with here with surface area. Trying to remember, surface area is like if you're trying to paint it, how much area is over the surface, which I know you're not supposed to define words with the words themselves, but that's what it is here. So we've got some 3-dimensional surface. It can be anything, complicated, simple, whatever. Call it S if you'd like. It's defined over some region R. Same thing we've been doing before, so some 2-dimensional region R is what we define this as. And we also have to make sure that we can find the partial derivatives, which hasn't really been a problem, but we have partial derivatives available. So we think about how we're going to go through and find this surface area. Instead of me drawing pictures here, I've got this, which does a nicer job of drawing pictures. Right now, the surface they have graphs is x squared plus y squared. I'm going to take this off. Okay, so that red surface is x squared minus y squared, x-axis, y-axis, and we've got just this parabola. It shouldn't be too surprising to look at that. And so what we're trying to do is go back and find the surface area of this. So the idea is, well, cut it into simpler shapes. If we split this up, this region, imagine looking down at this region. If you split this region up in the x direction and split up in the y direction, you're going to have a whole bunch of little squares on your region, right? So imagine looking at this guy from top down. Our region right now is a square. Doesn't really look like it, but I can't drag it any further.
Yeah.
Okay, but our region is a square. If we cut this up into a whole bunch of little pieces, we say, okay, well, for this little teeny weeny region, or a square on the region, what's this mapped to on the surface? We're eventually going to have a whole bunch of little parallelograms. And so that's what this is trying to go back and show here. So this blue surface is saying, okay, if we split this into 2 groups in either way, so just one split in x, one split in y, all right, we get this kind of really crude version of our paraboloid, right? But if you think about this, each one of these little pieces is the same in this case. It won't always be the same. But what shape is each one of these little pieces? Or maybe reword this. Do these pieces have any curve to them? No, they're just flat little planes, right? And if we think about the shape of each one of these planes, depending on the angle we hold it at, they're all a bunch of little parallelograms. Okay? Have we talked about how to find the area of parallelograms? Yeah, we talked about how to do it cross products and magnitudes, that stuff there. So we know how to find the area of this parallelogram, which means I have a way to approximate the surface area. How can we make this blue shape better or closer to the red shape?
Small.
We have more breaks or smaller little pieces here. So as we keep increasing the number of breaks that we make in this, our estimate gets better and better and better and better. And you can see here's the actual estimate computed above there. And that's pretty much what we're going to go through and do. We're going to say, okay, if I have an infinite amount of these little breaks here, my red shape and my blue shape are going to be almost identical. Okay, we're not going to have much difference at all in those two shapes here, and I've got a really good estimate of the surface area. So we're going to go through the notes and kind of try to fill those pieces in, but that's the idea. You have this region, you split it up, you got a whole bunch of little planes all over the surface. We're adding together the area of all those little parallelograms.
Is that kind of like Raymond sums?
Yeah, it's exactly like that. Yep, just with two variables that are changing instead of one. Yep, same thing. All right, we're not going to get into all of the math here because that takes a little longer than we need, but kind of an overview of what we just said here. So the idea is we're going to take our surface and split it into a bunch of rectangles. So split surface into, oops, we'll say a lot instead of an infinite, a lot of small parallelograms. Okay. And then what's special about those parallelograms is a couple of things. Each of those parallelograms always maps to just a little square in the region.
Just mesmerized.
Okay, so if you're looking from the top down, like we said, we make all those divisions. We have a whole bunch of little squares in this region R, and if we kind of follow those things up to the surface, we've got a whole bunch of little parallelograms all over the place here. Again, each one of those parallelograms is just a plane. Planes are nice and easy to work with. We can find the area of them without too much work there. So that's kind of what we're going to work with here. These small squares in our region R, they're all going to have an area of x times y. So depending on how many divisions we have, that's going to change. But whatever the change in x is, whatever the change in y is, which will depend on how many breaks we have there, that's going to tell us the area of each one of these little tiny squares there. The way we find the area of the parallelograms is a little more complicated. So to find the area of parallelograms, which is really what we care about. We want to add together those parallelograms. A small square, we don't care about adding together. We'll just use that to fix our notation later on. But finally, our parallelograms, which is really what we care about, because the sum of all those is going to give us our surface area. We need to recall that back in chapter 11. I don't know exactly what section it is. I wrote it down. 11.4. We said that the area of a parallelogram is going to be given by the magnitude of the cross product of two vectors for adjacent sides. And you can flip back to your stuff and do this. Don't worry about it too much right now. I'll just give you what the answer is. But hopefully that looks familiar. We have a parallelogram in 3D space, any two adjacent sides, find the cross product, find the magnitude. That's the area of the parallelogram. So what we need to do to fix this is we need a way to find those two adjacent sides in terms of our surface, because that's what these parallelograms are being generated by. And I'm not going to get too in-depth with that. If you want, I found a website that does a really good job of kind of explaining it and drawing a little picture for it. But eventually what we're going to get is this. So for our surface, eventually we can come up with that U is going to be equal to delta x, 0, and then the partial of x times delta x. And like I said, seeing where that comes from is not obvious. It's explainable, but I don't think it's really worth it for what we need to do right now. But eventually, we're going to come up with this. One of those sides of that little parallelogram is going to be given by whatever the change in x is, and then no change in y, just the 0 for that. And then the partial derivative with respect to x times the change in x. And if you're curious about it, feel free to send me an email. I'll send you that link, or I can try to explain it myself. And what we're going to come up with v is something pretty similar, only we're going to have 0 in the x direction, and then the change in y, and then the partial with respect to y times delta y. So as long as you trust me, that's where those comes from there. The rest of this should kind of fall into place pretty nicely. We won't go through and find the whole cross product, but you guys know how to go through and find cross product. If you were to go through and do the cross product of u cross that would v, eventually what we would come up with is this. So if we took the cross product of u cross with v, we would get a vector. Remember, because cross products give a vector, so we still get a vector out of this. We have negative partial respect to x times delta x delta y, negative partial respect to y times delta x delta y, and then just delta x delta y for the last term. Okay, which feel free to track your own, but we'd eventually come up with this. Okay. So if we go back and use that little piece up here, that delta x times delta y is just talking about the area on that region that we're changing. We can go back and factor those out because that'll be some kind of constant. Not really constant there, but that'll be approaching 0. As we have more and more and more divisions in this in both directions, the change in x and the change in y gets smaller and smaller and smaller. That's eventually just going to turn into our dx and dy for this problem. But for now, imagine going back and factoring that out. So really what we're left with is the delta x times delta y, which is not really a constant, but it's approaching 0, so it's kind of like a constant. And the vector we're left with is negative fx, negative fy, and then just 1. Okay. So if we go back and find the magnitude of this, and we're really close to the formula we're going to need for our integrand just now. Eventually what we'll come up with at that is this guy, the partial respect to x squared plus a partial respect to y squared plus 1, and then all times that delta x delta y. But we said delta x delta y is just change in area, so delta a, and so we'll stop there. So skipping kind of that really important step of why are u and v equal to this, but they do turn out to equal that if you look at the change in shape here, and then skipping all the analysis, but we end up with this. So it's not really a complicated idea thought to follow, idea trail to follow there, but the math is a little more blurry. Okay. So anyway, this is what we're going to do. We're going to say, okay, well here's the area of one of these little guys. We're going to add this together for all the areas, and like we said, Riemann sums. When we're adding together these infinite summations, that's where our definite integrals come from, and that's going to be what's responsible for this guy down here. So we're saying this notation here basically says that delta S, or I'm sorry, ds, capital S represents a surface area. We're adding together a bunch of surface areas, which isn't really super useful. So the second version of this, that double integral with the square root, that's the one we're going to go back and use. And hopefully that looks kind of familiar. There's pieces of this that we've definitely seen before.
So, okay, back to ds, that'd be your arc length.
No, little s is arc length, capital S is surface area in this book. So I know it's very similar, but if it was little s, you're right, it would be arc length. But capital S, this book uses a surface area. So saying you're changing your surface area, add all those little pieces.
That would almost make sense.
Well, and these are really strong related. I mean, if you think back to Calc 2, when you're finding surface area, it's all based on arc length. And so yeah, there's a lot of similarity between the two things here. And that's what I was going to mention. Hopefully this formula looks fairly similar to how we go back and find surface area in Calc 2. It's based on taking the square root of 1 plus the derivative function squared, which is really the same thing that we have here. Only since we're working on more variables, we don't just find one derivative, we have two partial derivatives we're working with. Okay? So hopefully it kind of makes sense where it all comes from there. I mean, really, if you don't remember any of this, that's fine. As long as you can go back and use this formula, that's okay. We will see a problem with this where sometimes the integrals are just way too difficult to do by hand. So this will be another one of those cases where it's too difficult to do by hand, approximate your calculator, I'll just ask you to set it up, same things like we had before. And sometimes changing the polar coordinates may be easy also. If we change it to polar coordinates, don't forget to go back and multiply by r. And then the other thing is you're going to take your function, and when you think about translating that to r and theta instead of x and y, you're going to find the partial respect to r squared and the partial respect to theta squared. So hopefully it's what you would expect to see, but we'll do an example where that happens in just a minute. Okay. All right, page 22. Find the area of the portion of the plane Z that is above the circle, that guy in the first quadrant. So the surface we're working with is this function Z. What is the shape of this guy? Kind of tells us. If I graph that, what does it look like?
Paraboloid?
Nope, not a paraboloid, it's just a plane. Okay, so we have just plane 2 minus x minus y.
Yeah.
I don't think I have any of these graphs yet. No, that's from, I don't know what that's from. Well, we'll let that think. It is just a plane now. 2 minus x minus y is just a plane. But they tell us we're doing it over that circle in the first quadrant. So this piece right here, this is describing our region. And that's fairly easy to think about the graph of that, just a circle with a radius of 1. And since we're in the first quadrant, we are just talking about this little section right here. Okay. Since our region of integration is circular, do you think polar or rectangular are going to work better for this problem? Yeah, polar coordinates are probably going to be better. And if you're ever not sure, just start at rectangular coordinates, and if it gets too difficult, try switching. And that's an okay process to do there. So let's set this guy up. Surface area, which I'm going to use SA and not just capital S, as the book uses. S is little s is 5s, so surface area. We'll have to go back and define our region, so I'll leave that blank for just a minute. And then for the integrand of this, we would need to go back and take 1 plus derivative with respect to x plus derivative with respect to y. So let's just start off in rectangular coordinates, not change it just yet, and see how this looks like. So 1 plus, what is the partial derivative of this function with respect to x?
2 minus 1.
Negative
1.
1. Okay, I have to take the derivative of this guy with respect to y, with respect to x.
Squared.
Yeah, we do have to square it. And then take the partial derivative with respect to y, which is also negative 1. Just square that. And then we'll keep it dy dx for now. We won't worry about order of integration just yet. So if we looked in rectangular coordinates, what would be our lower limit for y? I think back to the region.
0 to curve.
0 to that circle. And if you solve that circle for y,
1 plus 1 minus x squared.
Yep. And then limits of integration for x?
0 to 1.
And that is not wrong. I mean, that is a correct way to set this problem up. There's nothing wrong with doing it that way. However, like you guys said, yeah, it isn't too bad, actually. However, like you guys said, if you would want to go back and do some polar coordinates, that's a-okay, because we have limits of integration that are circular, so it would work out pretty well. But the nice thing is this integrand is just a constant. So 1 plus 1 or square root of 3 is what we're going to get there. This one isn't too bad to just leave in rectangular coordinates, at least for now. So square root of 3 dy dx. Oops, y. Antiderivative of square root of 3. If you can imagine this is a constant, just hangs around, so just kind of square root of 3 times y. And if you want to pull that square root of 3 all the way up front, that is a-okay. I didn't leave space for that, so I'll just leave it here for now, but that is a constant, so it can get factored all the way out. Now here's where we run into a little bit of trouble when we try to integrate that next step. So plugging in a 0 doesn't change anything. We're going to get this 1 minus x squared dx. How do we integrate that?
Don't you use trig substitution?
Yeah, this would be trig substitution. So if we have the square root of something like this, if we had an x outside of parentheses, easy, just go back and use u substitution. But since we don't, this would be a trig substitution problem. And like I said before, I'm not going to ask you guys to go back and do Calc 2 stuff. Recognize you could apply it if you needed to, but we're not going to do that here.
Would that be dy? No.
I have a question for you.
Yes,
Yeah.
Stephanie.
So if it's 1 minus x squared to like any exponent, like 1 minus x squared to like the 3, could you still use trig substitution?
Yeah, because when you do the trig substitution here, so which one would this be?
This would be sine, wouldn't it?
Sine, I think, yeah. So if you go back and let, however you want to do it, I don't remember the notation that our book uses.
I don't know how your book used it, but we used it where x would equal 1 sine of theta.
No, those are probably the same things you do here then. So if we went back and did that, yeah, any power would work, because the idea is when you do 1 minus sine squared, that's always going to equal cosine.
Okay.
Left off my theta there. And so cosine to any power, whether it's a fractional power or some other power, is doable there. So yeah, if you have something like that, you can't use the substitution. It doesn't matter what the exponent is, trig substitution would work. So if you want to go through and try it, go for it. There's nothing wrong with doing it that way. If you hit something like this on a test, you could go back and approximate. But actually, we can switch to polar coordinates now, and we can make this problem work. So that's something different than what we've done before. So let's try that. And like we said, we're kind of not too surprised to switch to polar coordinates. We said in the beginning we could have switched to polar coordinates because of circular region. So whether we do it then or we do it now, it's not going to change things too much here. So let's just go, let's see, do it in the middle of the problem. Sure, let's just go back to the beginning and start from the beginning setting this up. It's good to think about the region. So this region in polar coordinates will come to in just a minute. What's going to be the integrand? How are we going to figure that out?
2 minus x r cosine theta minus
R sine times all.
R cosine theta. Now,
That's
that is our z function, but is that going to be our integrand in this case?
No.
No, because our integrand is the square root of the derivatives and all that stuff there. So we need to go back and find the partial derivatives of this with respect to r and with respect to theta. So if we find the partial derivative with respect to r for this, what are we going to get? Negative cosine theta minus sine theta? Right, because if theta is just a constant, we just carry those guys around. And then the partial derivative with respect to theta is going to be what? Would be r sine theta minus r cosine theta, right? Okay, and so that's going to be what we have to plug into our original problem, which is going to make it look pretty busy, but it'll simplify down okay in just a minute. So for our integrand here, we're going to have the square root of 1 plus partial with respect to r squared, so negative cosine theta minus sine theta squared, plus the partial with respect to theta, r sine theta minus r cosine theta squared. And then don't forget, anytime we're converting, we have to have that r for our dr d theta. What would be the limits of integration? So for r, what would our limits of integration be?
0, 1,
And for theta?
0, and pi 2.
This actually simplifies down quite a bit. So if you were to go through, and we won't work this, I'll just give you the answer. But if you were to go through and simplify this down, eventually, what does this simplify to? Yeah, because you'll have cosine squared minus 2 cosine sine plus sine squared, and then something over there. It's a lot of work to reduce it down, but eventually does reduce down and should still just give you the square root of 3. Which sounds kind of mean to go this much stuff here and get the same thing that we had before. So think back to what we said here. When we went through and found this, all the variables were gone, right? So if we imagine taking just this problem here and converting this to polar coordinates, and ignoring the fact that we're doing a surface area problem, we just have this thing here, we're just going to convert this to polar coordinates. Our integrand right now, that square root of 3 constant has to hang around. We know when we go back and do these conversions, we have to multiply by r here, and then we know how to switch limits of integration. These limits of integration here just draw this same picture. So going back to the very beginning is a much more complicated way of doing this. Point is, you can convert to polar coordinates at any point in your problem there. You don't have to go back to the very beginning. You could, and this should eventually work out, but I don't want to spend the next however many minutes doing trig here. Eventually, this should reduce down to the same thing that we would get if we switched to polar coordinates in the middle of the problem here. Okay, and if you go back and work that, so again, if you just switch at this point to polar coordinates, or if you just approximate your calculator, I mentioned that would work too. Eventually what we get is square root of 3 pi all over 4. And with the fancy calculators, they'll give you exact answers. TI-84, approximate, that's okay. All right, again, on this one, the setup is important. Sure, I'd like to see that you tried, but on a test, if I don't want you to try, I'll just say approximate, set up and approximate. Okay, so good to think about the steps there, but they're kind of a mess in this one. Yes, Stephanie?
So if we were to convert at the square root 3, square root 1 minus x squared, since you know 1 is equal to r slash maybe r squared, could you just plug in r squared minus r squared cosine squared theta and then solve from there? Or does that just not work?
Say that again. I followed part of it, but then I started thinking about part of what you said there. So are you talking about from this step here?
No, up.
Okay.
One row up. When we convert at that point.
Okay.
Could you be able to do that, or?
Yes, you should be able to do that. That'd be fine also if you convert that point too. Yep. So you'd have 1 minus, and it kind of looked like trig substitution there. If we went back and let x equal r cosine theta, you're saying?
Yeah.
Yeah,
And then
that-
could you sub in r squared as 1? Would that work, since you know that r squared equals 1?
You wouldn't want to do that because r equals 1 just at the outside, but r doesn't always equal 1, so you don't want to go back
Okay.
and replace r squared with 1 there. You want to leave that variable there so that we can change and fill in the circle.
So you'll just have 1 minus r squared cosine squared theta inside the square root,
Mm-hmm.
and then you solve from there.
Yes.
Okay.
Yeah, so if you get bored and try that, let me know how it goes. I can't think through steps fast enough in my head, but that should work. You should be able to convert from that point too. Okay. So like I said, setup, make sure you understand the setup, whether it's in polar coordinates or rectangular coordinates, and then the answer we can approximate if it gets too difficult, which is going to happen a lot with these guys. You get some pretty nasty integrals with these sometimes. All right, so moving on from that one, find the surface area for the portion of the circle F, or portion of the surface F that is above the triangular region with those vertices there. The shape of this one probably isn't as obvious just to look at. 1 minus x squared plus y. Let's see. Oh, this is ready to go now. So there is the surface we are talking about in this example. Okay, and the region of integration we are working with is this little triangle. Let's just graph that here in the notes. I don't have a quick way I can graph that in the other program. 0. I should have fixed this and I didn't. All the z components on here are 0. Just ignore them. Okay, if you just want to look at this in 2 dimensions there, that would be a-okay. I don't know why I listed it that way. Ignore all those little zeros from the components. It's not wrong, but this is a much easier way to think about graphing that. So since they're all the same z components, we'll just look at this in 2 dimensions. So 1, 0, 0, negative 1, and 0, 1.
Oh, yeah.
So here's our region right here that we are working with. Okay. And then imagine trying to put that kind of weird curved surface over this. So if I line this up, so here is looking down on it the same way that we are graphed there. So imagine like this little triangle in here is what we're talking about. I don't know if you can see that. All right, so anyway, there's a kind of a picture of what we're looking for. Let's go through and do the math. Or at least get it set up. Yeah, this one's not a nasty one. It uses trig substitution and stuff. So we'll just get this one set up and we'll just give you the answer. We'll approximate it. All right. Polar coordinates or rectangular coordinates? Let's just decide that from the beginning and go with it instead of flip-flopping back and forth like last time. Polar or rectangular? Brett suggests rectangular. Do you guys agree with him?
Yeah.
Okay, there's nothing circular about this region. Don't bother changing it there. So let's keep it all in terms of x and y. We are going to need the partial with respect to x and the partial with respect to y. I'll note those off to the side this time since they're a tad more complicated. What is the partial with respect to x for this problem?
Negative 2x.
And partial with respect to y?
1.
So for our integrand, we're going to have 1 plus negative 2x squared plus 1 squared. We'll go ahead and just keep it dy dx. If you like dx, dy better, that's fine. Doesn't really affect things too much in this problem. Actually, dy dx is easier. Yeah.
Wait, don't you want to do dx dy?
If we do this dx dy, if we do the x part first, then we're saying we're making these left to right changes first here. And the problem with that is on the upper part of this shape, that negative slope line is going to control our x. And on the bottom part of this shape, a positive slope line does. So we'd have to split into 2 regions.
But y, oh wait, no. Okay.
Yeah, so this,
dy.
yeah, so dy dx will be a little easier on this one here. Even though it's vertically simple, still I do dy dx. Okay, so for dy dx, this guy down here is going to control our lower bound for y. We're not given an equation for that, so we need an equation for this line. But if you think through it, hopefully it's not too hard to see where it comes from. Oops, I tried a comma. If we go back and find the slope of this line is 1, y-intercept is -1, you eventually just get x plus or x minus 1 for that line. And then similarly for the top line, if you go back and find the equation for this guy, from the point 0, 1 to 1, 0, this ends up being -x plus 1. Okay, so without taking time to go through there, hopefully you guys are confident with that. So lower limit is x minus 1 in the bottom line, and upper limit is -x plus 1 for the top line. limits of integration for x or what?
0, 1.
And there we the setup. The first few steps of this aren't too hard. You can just simplify from the square root. So squaring both those factors and combining like terms together. And that isn't really going to save us or the calculator much time. It's just to kind of note how we'd start this. So 1 squared plus 1 eventually get 2 plus 4x squared. And then we start running into issues. Okay, so from here it's very similar to the last one. So like Stephanie suggested, this where we use trig substitution. If you want to factor out a 2 from both those terms, that's fine. If you want to just leave it as is, there's ways to work that way. But this would be another trig substitution problem. You'd use the tangent for this one since we're adding the 2 terms. And then proceed like that. But again, I'm not going to expect you guys to go back and do all that Calc 2 stuff. So note, could use trig substitution. But we won't. Okay, we'll just say if you get to this point, approximate your calculator. So about 1.618 is what the calculator gives us.
Shut up, Brian.
Did you write the exact answer for this one?
Don't answer me.
So how are the equations for those lines? You just
So y minus, yeah. So that's kind of the easiest way to get your equation from the line, that form there. So we go back and find the slope and plug things into this. So you're going back and finding volume and then line.
Where you could make through this line.
Oh, okay. Right, so for that one, we were given the surface of the plane. This one, we don't have the surface of the plane, but if we were told what plane was intersecting, we can go back and do it that way. But in this case, we don't have that information. We're just given the points where it hits at, so it's more like just a regular two-dimensional problem. But yeah, I see what you're saying now. Okay, yeah. All right, questions? I mean, we're not doing a lot of the mathy part of this, so hopefully the setup makes a bit of sense. 2 more to set up, and then we should be good with this section. Find the surface area, the parabola that is above the unit circle. This parabola, if you look at a graph of it, it's going to be shifted up 1 unit, and then the whole thing just opens up 1. That's just x squared plus y squared just moves up 1 unit. And so if we're talking about this thing above the unit circle, we can basically picture what that looks like. Still going to go back and graph that region because that's just what I do. So there's that region of integration that we are working with. And this one isn't restricting us to looking at just one quadrant. We're saying above the whole unit circle here. So if you try to visualize what the shape is, this could be a solid of revolution. I mean, if you think back to Calc 2, this would work here too. You essentially have this can on the sides, just regular cylinder on the sides, and that paraboloid scooped out in the middle. And then the bottom of it is about 1 unit high the whole way through. So we've got a can with a scoop taken out the middle of it. But really what we want to do is go back and find the surface area of that scoop. The sides we don't care about as much here. It's just that scoop that we made. What's the surface area of that? So let's set it up. Polar or rectangular?
Polar.
Polar are definitely easier in this case. Polar. Let's go ahead and rewrite our function before we get too far. How is z? How can we represent z in polar coordinates?
1 plus r squared.
Yeah, so z is just itself. And if you recognize x squared plus y squared, r squared, you save yourself some work. If you didn't, that's fine. Go back and plug in x is our cosine, y is our sine, and you'll eventually get to this point here. We need partial derivatives, so let's go back and find those now too. Partial respect to r is what?
Respect to r is 1. I mean 2r, sorry.
There you go, 2r. And what is the partial respect to theta?
0.
Yeah, there's no theta there, so it's also constant, so it's just 0. So if we set up our surface area, I'll come back to limit of integration in just a minute. My integrand is 1 plus the partial respect to r squared plus partial respect to theta squared, and then don't forget times r, since we converted to polar coordinates, and stick with the r to theta. Limits of integration for r are what?
0 to 1.
Mm-hmm. And for theta?
0 to 2 pi.
Mm-hmm. Now, since this shape is symmetric, you could go through and use symmetry and say, well, just from like 0 to pi times 2, or from 0 to pi over 2 times 4, but in shapes where it's not symmetric or you can't tell, that definitely causes problems. It's okay if you just do the whole thing like this, okay? And if you want to take shortcuts, that's all right, but this works out okay. Let's see if we reduce this. I don't think this one's too bad to do by hand. I'm trying to look through my notes real quick. This should be okay. We'll do this one. So what do we get? 0 just is gone, so that is 1 plus 4r squared. Why is this one so much easier to do without trig substitution?
Because the circle is perfect.
It's really similar to the last one, so why don't we need trig substitution here?
Because we have the r.
Because we have the r. Good. Okay, so u substitution. 1 plus 4r squared, which means du equals 8r d theta. Nope, r. Sorry, totally wrote the wrong thing there. We don't have that constant, so I like to multiply by its reciprocal, but again, like you said, we've got that r there, so we can just use u substitution. If you'd rather go back and find the limits of integration in terms of r, that is a-okay. I'm sorry, in terms of u, that is a-okay. If you want to just keep them whatever you're comfortable with, I don't want you guys to do it different at this point. I am just going to cheat and leave them as is and then go back substitute, which just feels like the cheater's way. But eventually, square root of u times 1/8 du. So what do we get? 0 to 2 pi is still there. We've got 1/8 times u to the 1/2's antiderivative is what? U to the 3/2, and times 2/3. So I'm going to back substitute since I didn't find the limits of integration. And also 1/8 times 2/3 is 2 or 24, so 1/12. All right. Which gives, I'm going to plug in a 1 squared times 4 plus 1 is 5, so 5 to the 3/2. And if we plug in a 0, we get 1 to the 3/2, so just minus 1. Which is all just a constant. It's a very ugly constant, but it's all just a constant. So the antiderivative of that is that big constant times theta, and then evaluated from 0 to 2 pi. So 1 over 12. 3/2 minus 1. So we should end with 1/12, 5 to the 3/2 minus 1 times 2 pi. But we can reduce that 12 and that 2. So 5 to the 3/2 minus 1 times pi all over 6.
You want to look like I'm not with you?
Look okay?
Yeah.
All right. That's it. That one's not too bad.
15.
Any questions?
No. Just
Okay, let's set up one more, and depending on how much time we have left, we'll either work through it or I'll just give you the answer here. All right, find the surface area of the portion of the hemisphere that is above the region bounded by, and then we're given that equation. I'm not going to go back and graph this one, but if you think about this, what's the radius of the hemisphere that we're talking about, of this surface?
5.
It is 5, okay, square root of 25. So we've got a hemisphere radius 5, and since we're just talking about the positive square root, we know we're just talking about the top half of this hemisphere. Tell me about the region that we're bounded by.
0 to 5.
Let me fix this. It's a circle of radius. Great, only radius 3 here. So what we're doing, if you imagine you have this hemisphere, and you're kind of like cutting a section out of the middle of it. So our circle, our region that we're talking about doesn't go to the end of the hemisphere. It's going a little bit shorter than that. So the shape that we would have if we were making a shape out of this is, again, like a little can, but have a little dome top. Okay. But we are going to go through and graph the region. It is, again, a circle. with a radius of 3 in this case here. We're not told we're talking about a specific quadrant, so it's the whole thing. So polar coordinates or rectangular coordinates. Polar coordinates are definitely going to be easier here. Okay, and also polar coordinates for our surface are going to help out a lot nicer too, because if we convert that surface to polar coordinates, instead of working at 2 variables x and y, we'll have just one variable, we'll have this r there, and that makes it a little nicer as well. So very similar to the last one. Let's go through and set this up. So in terms of r and theta, our function is going to be the square root of 25 minus r squared. We do need the derivatives of that, which are a bit messy, so we'll go ahead and set this up, but we'll just look at the answer. I won't make us go through and work all of it. So what is the partial derivative of this surface with respect to r?
-2r.
The square root of -2r.
Nope, gotta use the chain rule. Wish it was that easy.
Chain rule. Oh, whenever you write it, okay.
Yeah, so if you write it this way, maybe it makes it a little easier, so you have to go back and use the chain rule. So 1/2 comes out front, keep the base the same, decrease the exponent, so all that's a -1/2, and then what do I have to multiply that by?
The derivative -2.
And the derivative inside -2r. There you go. So if we clean that up a little bit, the 1/2 and the 2, we can reduce those guys. This is -r over the square root of 25 minus r squared, which is definitely not a pleasant derivative. Especially if you think about that, we're going to then take this and square it and put it under the square root. It gets pretty messy for this one. Okay. It is doable, but it gets pretty messy. If we find the partial derivative with respect to theta, what's that equal?
0.
0. Woohoo! Nice easy one there. So setup. Our integrand is going to be 1 plus the partial respect to r, 25, squared, plus the partial respect to theta squared, and then times r, since we're converting. Limits of integration for r,
0.
and limits of integration for theta.
0.
Okay. And there's the setup. All right. Yeah. Nice thing is the 0 is gone because 0 squared is just 0. And when we square that partial derivative, the square root is going to cancel out here. It actually looks a lot worse than it is. I'm not going to go through all of it. I'll give you a little bit of start here if you get bored and want to do it yourself, because I know y'all do math problems when you're bored.
Oh, yeah.
So if we go through and square that middle term, the negative will go away because negative to negative is positive. So we have r squared over just that denominator. And that actually helps out a lot. The next step from here would be if you were to add your fractions together. So if you find like common denominators, add them together, it actually simplifies down quite nicely to where you can end up just going through and doing u substitution. So you don't need any crazy rules for this one. You just need some algebra to fix your integrand, and then you can eventually just use u substitution. However, we won't worry about that. So we'll say algebra, u substitution, or calculator can do all that stuff too. Eventually 10 pi is what we should get. So feel free to try it sometime if you like it.
What are you being?
U will eventually be 25 minus r squared. Because when you combine those guys together here, you're just going to get a constant in your numerator. So you get just 25 with the numerator, I think, and so you can factor that out. And so you have like 1 over 25 minus r squared. So you can just, it works out very nice.
Oh, I see what you mean. 25 on squared plus r squared.
And get r squares cancel. So yeah, it really isn't as bad as it looks, but we won't worry about finishing that right now. Okay. So that is another use of double integrals. So we've got a couple different uses there. We've got actually next section talks about triple integrals, which are 3 times the fun of single integrals, but we'll still talk about similar uses there. You guys are doing a good job of finding limits of integration from what I can tell just based on the feedback in class and a little bit on the quizzes, and that's super important. So if you don't feel confident in finding limits of integration, let me know. Because that makes a big difference on how we can do the rest of this. So both in rectangular coordinates and in polar coordinates. If you feel comfortable finding limits of integration, you're probably not going to have too hard of a time in this chapter, because that's really the biggest part of it. But that doesn't make sense to you, or it's not feeling confident, just let me know. We'll work through it. Okay. If you guys have questions, let me know. No class tomorrow. As for the quiz on Thursday, let's see if I can give you a heads up of what to expect. Yeah, this one's good. So we'll just talk about setting up integrals. And Cole, how comfortable are you using your calculator to approximate these? Because you have only an 84, right?
Yeah.
Are you fine approximating these in your calculator? Have you tried it much yet?
No, I've tried, like the only ones that I've tried, it says that it can't do it. Like it just says error or whatever.
If you come across one of those, send me which one it is, and I'll see if I can figure out something to do to help you out there.
Okay.
But yeah, okay. So we'll just do setting up integrals. I was going to have approximating too, but we'll skip that since Cole's calculator given it fits. All right, but that's all. No class tomorrow. See you guys Thursday. Work on the homework in between. Okay?
All right.
Next info.
Yes.
The quiz is about setting up